Welcome to AI Paper Podcasts. Today we're unpacking motion attribution for video generation, a paper coming out of NVIDIA, Princeton, and MIT.
A really strong team, Jindy Wu, Despoina Pachaladu, and others.
They're tackling a massive, massive problem in generative video, the black box of motion. So here's the 1-minute summary.
Let's do it.
Video models like Sora, Veo, Wan, they're all scaling up like crazy, but we have basically no idea which training clips are responsible for specific motion.
Right, the existing methods just get confused.
Exactly. They confuse a static picture of a dog with the actual motion of a dog running. So this paper introduces Motive, a gradient-based framework that uses motion-aware masking to isolate those temporal dynamics.
It's all about the motion.
They use a tool called All-Tracker for optical flow, a single-sample gradient estimator for efficiency, and a super important frame-length normalization fix. And the headline result.
This is the crazy part.
Fine-tuning on just the top 10% of data that Motive selects outperforms fine-tuning on the full data set. It gets a 74.1% win rate in human preference tests.
That is a massive claim. I mean, beating the full data set with just a tenth of the data. That's the holy grail of data curation.
Yeah, it really is.
It basically says we're wasting compute on 90% of our training tokens.
It's efficiency, it's quality, it's everything we want. But before we get into the how and the architecture here is fascinating, let's step back a bit. We talk about data attribution all the time in LLMs, but why is it such a headache for video specifically?
Right. So in language models, or even, for images, data attribution is basically asking, if I boost this one training example, how does it change my output?
It's the who taught you that question.
Precisely. It's the blame assignment problem, or credit assignment if the output's good. And methods like influence functions, track-in, TRA, they work okay for static stuff.
Okay, so if I generate a cat on a boat.
It can look back and find training images of cats and boats, pixel similarity, but video adds time. And that's the whole problem. Traditional methods just treat video like a big stack of images.
They're seeing a volume of pixels, not a sequence of events.
Yes. The paper's example is floating. If you ask the model for an object floating, a standard attribution method might pull up a static photo of a lake.
Because it looks like water. The appearance matches.
The appearance matches, but there's no motion. It completely misses the bobbing dynamic.
So you get appearance matching, but not motion matching. You ask for a verb, and it gives you a noun.
You couldn't have said it better. And that is the exact gap Motive is trying to fill. They want to attribute the verb. They want to know where the model learned the physics of buoyancy, not just what water looks like.
Okay, let's unpack Motive's architecture then. How do they force the model to look at that verb? Because usually gradients are calculated over the whole input.
It starts with where the model looks. So component 1, motion masking. They use this dense point tracking system called All-Tracker.
All-Tracker sounds like a spy tool.
For pixels, yeah. It's an optical flow mechanism. It gives you flow vectors and confidence scores for every pixel.
So it tells you what's moving and what's just background.
Exactly. And Motive uses this to create what they call a motion-weighted loss.
And mechanically, what's actually happening when that gradient is calculated?
Think of it like you're highlighting a book. If you want to understand the plot, you highlight the action, the dialogue. You ignore the white space on the page. Motive tells the gradient calculation, ignore the static background. Only calculate influence based on the moving object.
That makes so much sense. If I'm learning how a ball bounces, who cares about the wall behind it? But there has to be a catch, right? If you just weight by movement, doesn't the model just pick the fastest moving things?
That's the immediate risk, for sure.
Yeah.
A Formula One car has way more moving pixels than a hand waving hello. If you just sum the motion, the car wins every time.
Right. It just becomes a speed detector.
It does. So they add a really subtle but important detail. They use min-max normalization on the motion magnitude.
And why does that matter?
Because it emphasizes relative motion within the clip itself. It normalizes the signal range. So a subtle floating motion, which is slow and rhythmic, can be treated with the same importance as a huge explosion, as long as it's the dominant motion in that clip.
Ah, so it levels the playing field. It's about the pattern of movement, not just the raw speed.
That's it.
Okay, so we have the mask, we know where to look, but calculating influence, usually that requires computing an inverse Hessian matrix, which, for these video models...
It's computationally impossible. Forget about it.
Yeah, we're talking about models like 2.1 with 1.3 billion parameters. You can't invert a matrix that size.
You absolutely cannot. So that brings us to component 2, scalability. They have to approximate. And they do it with a single sample estimator.
How much of a shortcut is that?
It's a massive one.
Yeah.
Normally, you'd average over thousands of time steps and noise draws. You know how diffusion works. You add noise, you do noise over, say, 1,000 steps.
Right.
Motive says, we can't do that for every single training sample. So they just fix a single time step, fix, and a single noise seed. Epsilon fit.
Wow, that sounds risky. Aren't you just introducing a ton of noise? If you pick the wrong moment, you're looking at garbage.
That was my first thought, too. But they did an ablation study, and they found a sweet spot. They fixed the time step at step 751 out of 1,000.
That is weirdly specific. Why 751?
It's roughly in the middle of the denoising trajectory. If you go too early, say step 900 plus, the image is just static noise.
Right.
There's no structure there. If you go too late, like step 100, the video is already formed.
So the motion is already baked in by then.
Exactly. The gradients at that late stage are just about tiny pixel cleanups, like fixing the texture on a leaf. But at step 751, the semantic structure, the actual shape of the motion, is being decided. The model is wrestling with, is this a bounce or is this a slide? Right then.
So that's where the concept of the motion lives.
That's where the signal is strongest for motion. And to deal with the sheer size of that gradient, because even one is huge, they use a projection method.
The fast food projection.
Love the name. It's based on the Johnson-Linden-Strauss lemma. And what it lets them do, essentially, is compress these massive billion-dimensional gradients down to a vector of just 512 numbers.
Wait, hold on. 1.3 billion down to 512? That sounds like you'd lose everything.
It sounds totally crazy, but the math holds up. The projection preserves the geometry of the influence. So if vector A is close to vector B in that billion-dimensional space, they stay close in the 512-dimensional space.
Ah, okay. We only care about the ranking, who's number one, who's number two.
Exactly. We don't need to reconstruct the perfect gradient. We just need to preserve the relative distances to compare them.
That's clever. So we have masking for focus, single sample projection for speed. But there was one more gotcha they found, right? A bug related to video length.
Yes. The frame length bias. This is one of those things that seems so obvious in hindsight, but I bet it caused them weeks of headaches.
So what was the bug?
Just that raw gradients are naturally bigger for longer videos. If you have a 100-frame video, you're summing the loss over 100 frames. If you have a 20-frame video, you sum over 20. The 100-frame one just has a bigger gradient by default.
So without a fix, the model just says the most influential clips are the long ones.
Exactly. It just becomes a fine, long video function that ignores quality, relevance, everything.
So how did they fix it?
Simple algebra, really. They just normalize the gradient by 1 over f, where f is the frame count.
It flattens the playing field.
It does. A short, high-quality clip of a bounce can now compete with a long, rambling clip of someone driving.
Nice. It's elegant. Okay, so they built Motive. They applied it to the WAN 2.1 T2V model on 2 big data sets. And then they set up this query set of 50 synthetic videos covering physics concepts. Bouncing, rolling, floating.
And this is key. They generated those query videos using VO3. They wanted perfectly clean synthetic examples of physics to ask the model about.
Wow.
No confounding variables from real-world footage.
Let's talk results. They compared Motive against random selection and full fine-tuning. We mentioned the win rate, but let's look at the V-bench scores.
The key metric here is called dynamic degree. It measures how rich and intense the motion is. Random selection scored a 41.3.
Okay.
Full fine-tuning, using all the data, got a 42.0. Barely better. Motive, using just 10% of the data, hit 47.6.
That's a huge jump. That is statistically significant.
It is. It essentially proves that 90% of the data was either redundant or actively harmful to the motion quality. By removing noise, the signal got way stronger.
I want to hear about the qualitative wins. What did the model actually find? This is where we get to see inside the AI's brain.
This is the fun part. So when they queried for float, like a cube bobbing in water motive, retrieved training clips of ocean waves, surfing footage, objects floating in pools.
Makes sense. What about for roll?
For roll, it retrieved a lot of clips of planetary rotation. And wheels spinning, of course. Yeah. Think about it. A planet rotating is the purest form of roll without any translation. It perfectly captured the physics of rotation. It ignored that a planet looks nothing like a wheel and focused only on the rotational dynamic.
That's fascinating. And it also did this negative filtering thing. It figured out what not to use.
Right. It found that clips with camera-only motion were negatively correlated with the physics queries. So where the object is still a NOCO, but the camera pans past it.
Wait, why is camera motion bad?
Because of parallax. If you pan a camera past a car, the car moves across the screen, but the car itself isn't moving. Its physics are stationary. If the model learns motion from camera pans, it starts making videos where objects just slide around unnaturally.
Ah, it's fake motion.
It's fake motion, and Motive successfully identified that. It also hated cartoons.
Right. Why cartoons? I think cartoons would have great exaggerated motion.
They do, but they cheat physics. They squash and stretch in ways that don't align with the realistic physics the model was trying to learn. Motive basically realized that if you want to learn bounce, a Looney Tunes clip is actually bad training data because the elasticity is all wrong.
That brings up a counter-argument the authors address, the motion-rich fallacy. Is Motive just picking the clips with the most movement? Like, is it just selecting Michael Bay movies?
That's the obvious critique, right? Maybe it's just a high motion filter. But they checked. The average motion magnitude of the top 10% selected by Motive is almost identical to the bottom 10%.
No way. Really?
Yeah. It's not picking more motion. It's picking coherent motion, motion that aligns with the physics of the query. A chaotic, shaky cam video might have high motion magnitude, but Motive rejects it because it doesn't look like a smooth roll.
That is such a crucial distinction. It's quality of motion, not quantity. Separating signal from noise in the time domain.
And that leads right into the implications for researchers, especially with cross-motion influence.
This was the heat map analysis.
Yes. They look at how different motion concepts overlap in the data. For example, bounce and float, they found, share about 45% of their influential data.
Why would bounce and float overlap so much?
Well, think about the physics. Both involve an object interacting with some kind of restoring force gravity or buoyancy and oscillating. It's a rhythmic up and down dynamic.
It was harmonic motion.
Exactly. The model effectively grouped them. But then you look at free fall and stretch.
I'm guessing those are pretty different.
Almost zero overlap,
Yeah.
like 12%. Free fall is unidirectional acceleration. Stretch is a deformation. The model correctly saw that these are physically distinct concepts.
That is wild.
It proves the model isn't just learning stuff moving, it's implicitly learning physics.
It's like there's a rudimentary physics engine being built inside the latent space.
Or at least a physics library of patterns. It's categorizing the world by forces, not just by what things look like.
Let's talk about the practical side then. Efficiency. If I'm a researcher listening, I'm thinking, great, but I don't have a cluster of H100s. How expensive is this to run?
The setup cost is non-trivial. Calculating the gradients for 10,000 samples takes about 150 GPU hours on an A100.
So a week on a single card.
It is, but it's what they call embarrassingly parallel. If you have 64 GPUs, it takes a couple of hours. And here's the kicker. That's a one-time cost. Once you've calculated and projected those gradients into that 512-dimension space, you index them.
Like a search engine.
Exactly like a search engine. After that indexing, querying the database for a new motion takes seconds. This enables what they call interactive curation.
So a researcher could just sit there, type explosion, see the top clips, realize they look fake, and then tweak the query to chemical combustion and refine the data set in real time.
Yes, it changes the whole workflow. Instead of train and pray, it becomes debug and curate.
It creates a real feedback loop. We've had this for text for a while. Now we have it for temporal dynamics. We can finally debug time.
That's a good way to put it.
Okay, so to summarize the Motive paper, it's a gradient-based attribution method for video. It masks the background to focus on motion, uses a clever single-sample estimator at step 751, and projects everything down to make the math feasible.
And it proves that less is more.
Yeah.
10% of high-quality motion-aligned data beats the full data set. It's the first real tool to debug the time dimension of these models.
So before we sign off, the provocative thought. We've been talking about physics of bounce, roll, float, very mechanical stuff. Could you adapt the same gradient masking technique to attribute something like emotional motion or narrative pacing?
That is the next frontier, isn't it? I mean, right now they use optical flow to mask for physical movement. But what if you masked for something else, like facial microexpressions? Could you attribute which training clips taught a model to generate a sarcastic smirk? Exactly. Or pacing. Could you define a mask that looks at the rate of cuts in a scene or the speed of camera pans to attribute something as abstract as cinematic tension? The math should hold up. The gradient doesn't care if it's physics or emotion, as long as you can define the mask.
Wow. If we can start curating training data based on emotional resonance instead of just, is there a cat in this video, we're going to see a massive leap in AI filmmaking.
It's the move from just simulating the world to actually telling a story.
And on that note, we'll leave you to ponder the physics of storytelling. Check the show notes for the link to the paper, Motion Attribution for Video Generation. This has been AI Paper Podcast. Thanks for listening.
See you next time.